So in general, optimization problem is expressed in the standard form that you have seen here. So in this case, we have, let me draw, we have an objective function. So in this case, this is the objective function where we want to basically objective function, which is the one that we try to minimize. So this can be, depending on some circumstances, some of these problems will be easier to be solved and optimally to be solved, which will be called convex. And some other problems will be non-convex, which are more difficult to be solved. And again, in general format, we have for a given variable, set of variables x, which is from x1 up to the xn, is a set of optimization variables. We try to basically minimize the f0x function, as you see here. And again, there are a certain number of constraints in this problem. So the first constraint is basically fix from I1 to the m. So we have m inequality constraint. So these are inequality constraints. Inequality constraints. And these make sure that the functions notated by fix from I1 up to the m are basically smaller or equal than 0. And again, there are equality constraints in this case, and equality constraints are notated here by h. And in this case, basically hix is equal to 0 for I is from 1 up to the p. And again, all these functions get the x, the variable, set of variables as the parameter. So that's why they are mapped from Rn to the R. So they produce a scalar value from the n, the input vector in the n-dimensional vector space. And again, the goal here is we try to find x star, which basically minimizes f0, our objective function, while satisfying all the constraints. And again, this is the general format. Again, is one more time. So f0x is the objective function. So we'll see some different subtypes of these optimization problems depending on what our f0 are. And there are fi functions, which are basically inequality constraints. And there are hi function, which is basically equality constraints. And this is the general form for optimization problems. And in this case, there are these optimization problems, and special type of this optimization is a convex optimization. And in convex optimization, basically all these constraints and the objective function is convex, so that we can, the optimal solution that we find x star will be the global optimal solution. However, for non-convex optimization problems, the optimal solution we find may be a local optimal, meaning that it doesn't need to be a global optimal solution. So here are some examples. So in this case, basically the convex optimization is used in many areas. So for instance, for electrical engineering, these are just examples from both finance and non-finance. So for instance, there is an example of circuit design. So in this case, basically for designing the circuits, there is an optimization is called signal processing. In terms of the filter design, it's again called. For communication systems, so designing the transceivers and basically designing the beamforming. So in terms of the power control, again, this is electrical engineering. So these are all called. In financial engineering, there are different applications as well. So one is a portfolio design. So portfolio is basically different number of or set of assets, which is basically, we'll see, that tries to maximize the return and minimize the variance, which is one form of risk. And another application we'll see is basically index tracking. In index tracking, for instance, assume that we are having S&P 500 index. So S&P 500 index. And in this index, there are 500 constituents, such as from Apple, Microsoft, For instance, I'm just writing the tickers. So these are the names. AAPL is a ticker. MSFD is a ticker for Microsoft. The Verizon, for instance, Verizon is another company. V is for Verizon. And in this case, there are 500 companies. So instead of buying, and we try to track the index, we try to have the same performance as index. So that's why we need to, first of all, one solution is allocate 500 securities or buy 500 securities, and then allocate their weights according to the index. That will be one solution. However, there are other solutions. So instead of buying 500 securities, we try to find the 50 securities or maybe 10 securities that will give us the same characteristics of the index. So in this case, we try to replicate the index by using the subset of assets. So instead of 500 assets, in this case, that problem becomes index tracking. We'll see this problem, and that's another example in financial engineering. And again, the applications are in machine learning. For instance, convex optimization is also used in support vector machine. And most of the algorithms that we have seen, like maximum likelihood estimator, least square estimator, and other estimators, are basically in machine learning expressed as an optimization problem. And again, there are other examples as well, like biomedical applications, robust design under uncertainty, image processing. But here we'll be mostly interested in the financial engineering examples. And again, if you look at the formulas, like how the problems are formulated, and the optimization problem has three basic elements. One is the variables, the other is constraints, and lastly, it's the objective. So the variables are the variables that are unknown, as you've seen, and constraints are as we go back. So they are, the constraints here are Fix and Hix, which is expressed in terms of the optimization variables. And lastly, the objective. And objective here is F0x. So these three components define an optimization problem. So if you look at some of the examples, first is if you look at device sizing in electronic circuits. So for instance, the variables are device widths and lengths. So in this case, we have a bunch of devices, and we try to size the devices in order to basically minimize the power consumption in a given 2D area. And the aim is to basically minimize the power consumption. And the variables here are device sizes, device width and length. And in this case, there are a bunch of limits, like there are manufacturing limits, there are timing requirements, there is a max area requirement. So these are all requirements, and they need to be satisfied by using device sizing in the electronic circuits. And another is portfolio optimization. So in portfolio optimization, so what we have here is we have different assets. So in this case, assets are, for instance, can be equities. For instance, Apple is an asset. Apple stock is an asset. So these are called equities. And this is one type of equities like stocks, or in Turkish hisse senedi. So one thing is, in this case, we can invest in hisse senedi, or we can have bonds, in Turkish bono. So for different companies or the countries, we have bonds, and we try to allocate differently to different bonds. So for instance, we have A bond, we have the bond from Apple. So Apple basically bond, Microsoft bond, just as an example, and 3-month treasury bill. So this is another bond. So this is 3-month treasury bill, which is from the government. So in this case, by given these assets, historical correlations, we try to allocate certain amounts. So for instance, we want to say Apple is like 40%. Microsoft is like, I want to invest 30% of my money in Microsoft and bond. and in 30% money in 3-month treasury bill. So in this case, we are interested in finding such allocations or such a percentage of weights to be allocated, and it will correspond to the amounts. And in this case, we want to basically minimize one objective we're interested in is minimizing the overall risk or the variance. So we try to minimize the variance of all stocks. And in this case, the variance is also used to model the risk in portfolio optimization. So we try to minimize the overall risk given certain constraints. And there are certain constraints here. So one constraint is minimum return. So for instance, we want to say that at least the return of a stock should be at least 10%. So we can have such minimum return on investment or maximum investment per asset. So for instance, for each of these variables like Apple, Microsoft, or 3-month treasury bill, so we can say that we can invest at most 40%. So there will be another constraint we have in the portfolio optimization. There are a bunch of constraints. So for instance, we can have a budget constraint. We can say that we want to invest, let's say at most $10,000. I'm just making it up. Or for instance, again, we may have a minimum investment per asset constraint as well. So we can say that, okay, we want to invest at least 10% for each security. And given these constraints, by formulating this as an optimization problem, and we'll see in detail how we can formulate an optimization problem, we solve the optimization problem and we get the amounts that needs to be invested in different assets. So in this case, like assume that it will be 40%, 30%, and 30%. So this is an example for formulation. And let's look at an example in power control in wireless networks. So assume that we have n logical transmitter and receiver pair. So in this case, there are n receivers and n transmitters. And this is a wireless network design. And in this case, we want to design the power allocation where each receiver gets from the transmitter such that each receiver receives the minimum interference from the other links. So we want to basically design how much power we need to allocate to the transmitters such that each receiver receives the minimum interference from the other links. So this is the problem. And again, the problem will look something like this at the below, which is this maximization problem. And again, this is a domain-specific problem. So this is just an example. It doesn't have to do with the course content. So in this case, the signal to interference plus ratio in the ith receiver is defined as here, which is Pi is the power used by the ith transmitter. Gij is the path gain from transmitter J to receiver I. And again, sigma square is the noise power at the ith receiver. And in this case, we try to maximize the weakest SNIR signal to interference plus noise ratio subject to the power constraints. So in this case, we have a maximum power. So we cannot assign a power greater than Pi max to each Pi, which is the power for basically instrument, power for ith transmitter. And these are above limited by basically Pi max. And in this case, the objective function is basically Pi times Gij divided by for all others interference plus the noise power. So in this case, for among them, we try to maximize the weakest one and the power constraints. And overall, the formulation is like this. And again, this formula is non-convex. We'll see in detail. So this is not a convex formula. And for now, this is not a convex formula. And in this case, meaning that the solution found is a local optimal. And it doesn't need to be, or it's not guaranteed to be global optimal. it's not guaranteed to be global optimal. So this is not guaranteed.